Thanks so much. It's a pleasure to be speaking after all those really interesting talks. Though you'll hear some similar themes to what has already taken place, and a couple new ideas in terms of thinking about competition. Uh, when we think about technological change, one framework that we use in economics is to try to identify which particular, like for that technology, what's gotten better, faster, and cheaper. And so there's work by Nordhaus and Bresnahan that talk about computing. And as computers got better, they assert the major change in the world was in terms of the cost of arithmetic. Your ability to add and subtract got better and better and better to the point where today we use computers for problems that you never would have thought of as addition or subtraction questions. Um, the early applications of machine computing, of machine arithmetic, were for good old-fashioned arithmetic problems in terms of calculating the trajectory of of flight and in terms of accounting. But as that machine arithmetic got cheaper, we started to use it for music and mail and pictures and all sorts of other things that we never used to think of as arithmetic problems. With the rise of the internet, Hal Varian and Carl Shapiro pointed out in their book, The Information Rules, that the internet enables cheap search and cheap transportation of information. Catherine Tucker and I, in a JEL, Journal of Economic Literature, also pointed out that it ended up reducing the cost of copying information, of tracking information, and of verifying information. And so that name information rules was this, the rules of the information age, but also that information is in charge. That was sort of the double entendre in the book title. But it is, it points out that certain things got cheaper, and that is under the hood what's transforming the economy. Today we're talking about artificial intelligence. And my co-authors and I, Jay Joshua and I, said, under the hood, what's been going on in artificial intelligence for the past 20 years, most noticeably since 2012, has been advances in computational statistics, in the ability to fill in missing information. And so we frame that as a drop in the cost of statistical prediction. And that's the theme of our initial book, Prediction Machines, and more recently of Power and Prediction. Uh, that intuition that AI is doing prediction is useful for understanding the first wave of what happened with AI in business applications, as in perhaps the first large-scale business applications were in banking and insurance. For example, if you're a lender, you want to know if somebody's going to pay back their loan. And increasingly, lenders have been using machine learning tools. They've been using AI to predict whether someone's going to pay back the loan. But just like with arithmetic, as machine prediction got cheaper, we realized there's a bunch of things that we never thought of as prediction problems that can be solved with cheap machine prediction, like language translation, diagnosis, writing, drawing, and coding. Never really thought of machines that write, draw, and code or we never thought of the human actions of writing and drawing as prediction tasks, but that's what they are. You're filling in missing information. If you ask for an astronaut on a horse in the style of Andy Warhol, you get an astronaut on a horse in the style of Andy Warhol. How do you get that? It's not a search engine. It's instead using data, because it's computational stats, it's statistical prediction. It's using data on astronauts, data on images of people on horses, images of data on the style of Andy Warhol to predict what you're looking for when you ask for an astronaut on a horse in the style of Andy Warhol. Now, if a machine instead is trained on data from what's going on in our scientific journals, then in principle, that prediction task can lead to that underlying prediction technology can lead to a real scientific transformation. So Dario Amodei has this fantastic essay called Machines of Love and Grace. Amodei is the CEO of Anthropic. And in his essay, he provides an optimistic scenario of what AI could do. And fundamental to that optimistic scenario is we all now have access to the entire scientific literature. As in, we have access, he frames it as a country of geniuses in a data center. We have PhD level and beyond um, intelligence, knowledge, that in response to a query, we can get, or at least will soon be able to get, a thoughtful response. As in, we have a query and it fills in the missing information of that response. So, given machines that can draw, write, code, and synthesize, and perhaps even create by filling in missing information, extraordinary knowledge, it should be no surprise that lots of people are thinking about AI as potentially the next general purpose technology. And in many ways, the other speakers were all starting from the premise that AI, in many ways, is a general purpose technology. What distinguishes general purpose technologies from other technologies is that, yes, they are useful, like other technologies. Yes, they are used in lots of different industries, like other technologies. In addition, there is a positive feedback loop between the producing and using industries. And so what distinguishes a general purpose technology from another technology is the producing industry. In the case of, say, computing, the semiconductor industry, creates innovations that then lead to downstream innovations in peripherals and software and how to apply those, the co-invention required downstream that Diane Coyle referred to, that then in turn leads to further upstream innovation in in how chips are made and how computers operate, which then in turn leads to further downstream innovation. So in our standard growth model, like our 1950s solo style growth model, in the long run, there's no growth. What Bresnahan and Trachtenberg pointed out, that one way to get growth, to get outsized growth from one technology, is that if that innovation leads to downstream innovation, which leads to upstream innovation. So you have this feedback loop that still in the long run there until the next innovation comes along, there is no growth. But it means that each general purpose technology has an outsized impact on productivity relative to other technologies. Florenta Theodoridis and I have a paper that suggests that machine learning is likely to be the next general purpose technology, along with, or at least relatively likely to be the next general purpose technology, along with a series of other data science related tools. The real challenge in writing this paper is we realized that GPTs, general purpose technologies, can only be discovered, at least by the definition, after they've already widely diffused and the feedback loop has happened. And so if you want to rigorously figure out whether something's a general purpose technology, you have to wait 40 years. Okay. And that's frustrating. And so all we can do is look for these hints early on. And in our paper, we say relative to a set of other emerging technologies, AI or machine learning is likely to be a GPT. Now, I want to turn to a quick discussion of market power. And so the rest of this talk, I want to talk about, I'm an IO economist, and I want to talk about competition in AI. And the key thing is to recognize that for this feedback loop to get going, we need downstream innovators to trust enough that the upstream will keep innovating and won't price them out of the market. And we need the upstream to then feed into the downstream. So we need that feedback loop to happen. And I'm worried. Think AI is our best chance to have a massive productivity improvement overall, and productivity determines our standard of living. So my worry is that we don't have enough AI. But I think it's still an open question whether we will see competition, or whether today's largest tech companies will be able to extend their market power to emerging markets. And if that happens, the feedback loop may never get going. There's lots of good news. The good news, for example, is that we currently have competition. You heard earlier today about DeepSeek and Gemini And we already know about OpenAI and others. There's a lot of different companies, some established and some new, some closed, some open. This is, and then there's lots of other companies building specialized applications in driving and banking, financial services, graphic design, and healthcare. So there's really good news that we have lots of participants. There's also good news potentially on the cost structure of AI. So yes, there are fixed costs to setting up a model, but there's non-trivial marginal costs in terms of compute power and energy. And earlier, we heard discussions about how do we think about those um, demand for energy and the cost of energy. But if there's non-zero marginal costs, then many of our standard models can apply here, um, unlike the sort of platform-based software industry that we saw. And it's still an open question about how this is all going to play out, whether the fixed costs are that high that the positive marginal costs are still effectively zero or not. But there is good news that with positive marginal costs that may even be significant relative to fixed costs, that it's less likely to be a winner-take-all type market. There's good news on open models because we've seen open models mean that the laggards can be a few months behind the leaders, which then means sustainable market power will be pretty tricky. There's also good news once you remember that these are prediction machines, in the sense that while more data is better, there are decreasing returns to data in a statistical sense. Okay, so right, so if you think about textbook economies of scale, we get increasing returns, but data, we know that predictions improve in the square root of n. And so for any given use case, the marginal impact of a particular amount of data is decreasing in the amount of data you have. Now, there's going to be threshold points on which you need enough data to generate a new use case. But fundamentally, there are these decreasing returns to scale to data conditional on a use case. So it's not all good news. There are things to worry about as well. So probably the central thing to worry about maybe is what Sutton called endogenous sunk costs. When an industry begins, entry costs can be low. But as the market leaders compete and the technology improves, it becomes harder and harder to catch up to the frontier. So the dynamics of competition can often, in technology markets, lead to a natural oligopoly. Typically not a monopoly, but a natural oligopoly where a new entrant is going to have to spend billions and billions and billions to catch up to the market leaders. Sutton, in his 1998 book, documented that this occurred in a lot of technology industries already. And there's reasons to worry that this same phenomenon might happen with AI, where we're seeing billions and billions and billions being spent. And it's an open question whether that's going to lead to sustainable competitive advantage for the few companies that get ahead, in a way that Sutton documented in airlines and for a long time in computer chips, etc. Now, secondly, while on the reasons to worry, while there are decreasing returns to scale for every use, new uses can be found. And Posner and Weil argued that such new uses can create this stepwise function in terms of minimum efficient scale that temporarily can create market power with each jump. Finally, to the extent that there's learning from feedback, then the feedback loop can push against the decreasing returns to scale in data. And so this is an argument that Google and Microsoft have been having about the advantage of Google search. And there's suggestive evidence, going both ways. But the story here is when the feedback loop is fast, then the story is when the feedback loop is fast, you having more data gives you the ability to have even better predictions, which then in turn gives you the ability to have more data. Two more things to worry about. Another thing to worry about is regulatory pushes to monopolization. So if the regulatory environment is focused on other harms and not competitive harms, then we know from theory and a number of research in other contexts that small administrative costs can deter entry, and regulation that restricts who can enter and how they enter and places a burden on new firms can lead to a force to market power. And there's plenty of evidence, for example, that GDPR and privacy helped the dominant players do even better, at least in Europe. Now, last thing to worry about is tying. So AI is going to be a complement to many other information technologies. It already is, from office productivity software to cloud services to chips, et cetera, et cetera, et cetera. And so if the AI is tied to other services with a dominant company, for example, the companies that own the interface between the user and the AI, this could both reduce adoption and increase industry rents. And all this, of course, depends on an endogenous regulatory environment. And our newest NBR AI book is coming out soon, The Economics of AI, Political Economy, that emphasizes the importance of the endogeneity and the importance of the regulatory environment, understanding the competitive future and also just the future of AI writ large. So AI might be the next general purpose technology. It's not making decisions yet, but that can be blurred. But under the hood, it's prediction technology. There's good news on competition, open source, and diseconomies of scale and data. But there are things to worry about with respect to other ways that data can enable market power in terms of AI regulation and in time. Thanks so much. We've got time for a question or two.